Come on, come here, boy. Come on. You freaky dog. I don't need to analyze. Every word that comes out is a lie. Make it look like it's so ice. You won't make it to the finish line. Now if you gotta know the truth was gonna let you go. You was fine, never mind, unpredictable.
Hey, welcome everyone back to another Toolbox Tech Talk.
Sharing secrets here, which really was quite your life. Basic bullets, getting bullets.
Well, if you're wondering what the white noise is back there, it's rain. It's absolutely pouring with rain here. We really need it. It's been a drought for Melbourne, which is kind of generally a wet sort of place. We call, a couple of months with not much rain a complete drought, but it's pretty dry and crackly out there, and it has been causing a few bushfires. So my thoughts go to those people in Montrose. I believe there was even a house lost yesterday in a house fire as a result of the bushfire, in Montrose. Yeah, just urban Melbourne. There you go. So, g'day everyone, and hi Bob, good to hear from you. Bob, I think you're probably in China at the moment, maybe? Yeah, you're probably one of my most distant viewers at the moment, and I see Charles from Waiheke, you're there too, great, good to see you, Charles. Hey, wow, that rain is really intense. You're going to just have to put up with it. I do have a tin roof above me. I've got some sound insulation, some spray foam on the inside of the roof, but it's not really perfect when we've got a massive storm. So yeah, welcome everyone. Now today is a little bit different from my usual Toolbox Tech Talk, which tend to be very technical, lots of excerpts from standards, and we burrow deep into clause numbers, etc. Today's really more philosophical about going off-grid and some of those considerations. I often think that it's, some people think of it as a fairly lightweight choice. They go, oh gee, this property looks very appealing, purchase price is pretty good, it's got no power, but that's no problem. I've seen you can get a grid tie system for like $5,000 on a Friday afternoon, so surely that's all we need plus some batteries. So actually understanding the reality of off-grid is kind of what my Toolbox Tech Talk is all about today. So before we dive too deep into it, and g'day Gian from Sydney. Great to have you on board again. You're one of my regulars, you and Charles. So I won't run through the usual announcements around Solar Cutters Roadshow. They're well underway now. So yeah, if you're wanting to attend one of the Solar Cutters Roadshows, go to their website, solarcutters.com.au. And of course, we're inching closer to one of my favourite events of the year, the Smart Energy Expo in Sydney on the 9th and 10th of April. That just starts after my birthday, everybody, the day before. Hint, hint. So yeah, Smart Energy Expo, I'll be there. I'll be in my bling, don't you worry, and I'll be roaming around making lots of content. Okay, so what should we talk about? Everything off-grid, that's kind of what we're going to be talking about. And I've got basically some slides that I've used for a presentation earlier in the year. So I'll use those as kind of the basis for today. Whoa, that rain is insane. Okay, so I'm trying my best to see if I can noise limit this a bit more. No, I don't think I can. I'm just having a cloud burst over the top of me. All right. So let's dive into it. Everything off grid. What I call everything off-grid is it's more than just looking at the standards and compliance. It's also design, and design comes down to a lot of personal choices. So people often think it's all about the electrical side of things off-grid, but no, it's not. There's a lot more to it. I like to kind of start with just thinking about off-grid living. What do you expect? Are you prepared to live like a caveman, or do you want to just have a normal life without grid power, but with your own standalone power system? So that's kind of one of the choices. I mean, I went off-grid in 1991. I think I've told people this story before, kind of by accident. In a big rush of property boom in Sydney, me and my then partner, we bought this property off Men at Work, the Aussie band, who had a little getaway house in the Blue Mountains. And honestly, we didn't know it had no grid power. So that's how I became an accidental off-gridder. And I knew enough to be dangerous because my background in electronics. I made my own inverter from parts, got some secondhand batteries from a Telstra site that was decommissioning them. I got 3 SolarX 75-watt panels, which cost $800 each. Can you believe that? And that was my off-grid system. And it was pretty cobbled together, I must admit. I'm almost embarrassed by what I did back then. So you could say I started at the bottom end, somewhat close to the caveman kind of system. We had very minimal amount of power. And we relied heavily on a backup generator for things like washing machines or any large loads. So the quality of life, even though the setting was wonderful, the quality of life for electricity was pretty marginal. We had a gas fridge, and if anyone's ever had a gas fridge, they know that A, they cost a lot to run. I mean, the price of gas means that a 300-litre gas fridge costs you $1 to $2 a day in gas. Think about that. Say $1 a day, it's $365 a year, maybe as much as $700 a year just to run your fridge. Makes an electric fridge and solar look very, very appealing. But anyway, that was the thing back then, was gas fridges. They're also not very reliable, especially in hot weather. Christmas would come, hot weather, that fridge full of food for Christmas lunch, and it was struggling. It was really struggling. So yeah, those days hopefully have passed, of the days of gas fridges. They were also incredibly expensive for what you had got. So yeah. The other thing to consider is there really an option? Do you have access to grid power for money, like you pay to run the poles and wires there? And I often say to customers who approach me about an off-grid system, I say the first thing I'd like to say to you is, have you got a quote to connect to the grid? It's nice to know what you as someone selling an off-grid system know what you're competing with. And where I live in Victoria, unless there's power to the property, there's just wires in the street, you're often up for like about $32,000 just to connect. So there's your starting price, plus your undergrounds back to your house that you may or may not have built yet. So yeah, it gets north of $40,000 pretty quickly just to connect to the grid. And then you've got bills for the rest of your life. So it's good to know what you're competing with. Some other distributors have quite low connection costs, so if they're around the $10,000 to $16,000 mark, you might be saying, well, maybe it's better if you just connect to the grid, unless you really are passionate about being independent. So qualify the customer. Don't just assume that off-grid is the only choice and the right choice. So the design criteria, I'm basing all this on an Australian New Zealand standard, AS 4509. Part 2. So Part 2 is for design, Part 1 is for installation. Part 2 was last published in 2010, and we're working our way through rewriting both those parts right at the moment. They're well advanced, so we should actually have a new version. But it won't be a complete change, it'll just be an update and bring things in like AC coupled solar, which was kind of missed out back then in 2010. It wasn't so common. So some of the general criteria around design is what is considered, and that includes things like assessment of energy services and energy resource selection. Now, what do I mean by energy resource selection? Kind of sounds like a utility thing. What I'm saying is, what does your design, what does your installation or your home need? It probably needs things like water, heating or cooling, cooking, electricity for appliances, lighting, etc. But not all of those need to be in the electricity budget. So, for instance, heating. If you live in a southern part of Australia or much of New Zealand, heating can be by other means. Now, I wouldn't recommend gas because that's going to be really expensive, but things like wood are quite viable. Even, I hate to say it, if you have a bit of coal lying around at the back of your property, there's another non-renewable resource. Because I grew up in New Zealand, I briefly rented a place on the west coast of the South Island, and there was a coal mine just up the road from me, and they would literally drop a truckload of coal, enormous blocks about that big, off the front garden for a pittance, because it was just, wholesale pricing, I guess. So just think about your energy resources. Now, I would probably veer philosophically towards renewable resources. Like if you can grow wood, wood is actually a carbon neutral source of energy. In fact, it's pretty amazing when you think about the energy density of wood. So hardwood in Australia has a lot of thermal energy when it's released. So 1 kilogram of a hardwood timber will release approximately 4 kilowatt hours of thermal energy. That's pretty amazing. 1 kilogram is just a little block like this of wood. One is 4 kilowatt hours of energy. So if you have access, and this is probably people living in a more rural setting, to a sustainable source of wood, it's actually a pretty good choice for heating. Some people even use it for cooking as well. I lived for 15 years using a Stanley cooker fired by wood, and it's actually a wonderful experience. It kind of warms it's the heart of the house. It warms the kitchen, and it gives you a huge surface to cook on with a graduated heat from one side to the other. But then again, you do have to keep it fed with wood, and it also heated water. So why am I telling you about wood when you might be thinking about solar and batteries? Because with a resource assessment, you should consider having a diversity of energy sources if possible, so that you're not totally reliant on just one source. Now, this kind of brings me to one of my favourite little diagrams. Now, if there's any psychology students out there, you may have heard of this one. It's called Maslow's hierarchy of needs. So let me just get Mr. Maslow out here. Where is he? Okay. I've got my overhead. There it is. And bring it online. Right. So this is a little pyramid. Now, Maslow wrote this as a psychologist back in, I think, 1943. And the idea is the needs of a human. And at the bottom are the most fundamental needs, and at the top, the least fundamental but possibly very desirable. Now, let's think about this in terms of energy. If you put all of your services into the electrical budget, and you are reliant on electricity for just about everything, heating, lighting, pumping, etc. Let's see what happens. Now, air. How fundamental is air? Well, you can last a few minutes without air, but that's about it. So air is extremely fundamental in terms of hierarchy of needs. If you turn off your electricity for your standalone power system, yes, you can still breathe. So we'll give that a tick. We've got a happy face there. We still can breathe air. But we've got a pressurised water pump. A water pump that creates pressurised water from a rainwater tank that's actually lower than the house, so you can't get water into the house. So we've got no water because the power's gone off. Of course, our fridge has failed, so our food will probably spoil within a short period of time. If we're reliant on electricity for heating or even cooling, like reverse cycle air conditioning, we've lost that. It might be difficult to sleep at nights because it's too hot or too cold. That's not looking very good. And our sense of security, well, that can be all sorts of things, including things like security systems, right through to whether you feel safe at home. So this one's probably a question mark, whether electricity will ruin your sense of security. But having lost power now, and you've got no water, food, warmth, and you're a bit sleep deprived, your friends don't come around anymore, and you've lost a lot of respect. So it looks pretty bad, doesn't it? If you lose electricity, and so if you put everything into the electricity budget, you're very reliant on all of these things based on that system continuing to work. So that's why a resource assessment is actually a really good idea, and think about some other options. So one of those is, let's take water for instance. Now, pressurised water really is fundamental to operating things like toilets, showers, sinks, etc. But if you have a house like here, and this is your house with the solar panels on it, and you've got a property with a little bit of slope on it, and you put a nice big water tank up here, and if you pump water with surplus solar energy, so it's there's plenty of solar energy in the day that you can't use, so you pump water from a storage tank that might be your rainwater tank next to your house. So that's your rainwater tank there, and you're pumping it up to a storage tank up here, but it's a two-way flow system, so that means when you turn a tap on in the house, you've got a return pipe, so I should do that a different colour. That means you can flow water back down that system to the house. So you've now got pressurized water. How much pressure do you need? So for every 10 metres is 1 bar of pressure, or how many kilopascals is that? I can't remember. But anyway, ideally you'd probably want about 20 to 30 metres of head to get reasonable pressure for things like, modest flow, shower heads, etc. But that does mean if the electricity goes off, you still have water for flushing toilets, taps, and other services. So that's one way of not putting all of the electricity budget into water. Also, you can still have a pressure pump on the end of this pipe coming back down from the tank. So it may be the tank only provides you with a modest amount of pressure, maybe 1 bar, just enough to flow to run taps, but you can boost it to mains pressure with a pressure pump. But if the pressure pump can't run because there's no electricity, then you have a bypass valve. You can bypass the pressure pump and just let gravity provide service to the home. So there you go. That's another option. Okay, so coming back to, where are we? Structural assessments here. So assessing electrical demand. Hang on, have I covered all the resource assessments? Oh, yes, sorry. The other one is looking at your renewable energy resource assessments. So I've already mentioned wood, for instance, but there's some obvious ones like wind, hydro, solar, right? Pretty obvious ones there. Now, when you're doing an assessment for, say, anything other than solar, it does get a bit complicated. So wind, for instance, isn't quite as predictable as solar is. Solar follows basically the seasonal cycles in terms of average amount of solar energy, and it's well recorded. It doesn't actually vary a lot from year to year. You'd be amazed. You might say last year was really dry and this year's really wet. But actually, in terms of solar radiation, the average per month doesn't vary that much. So when it comes to wind, it's quite complicated now. Here's a pocket sort of view of wind. You need to understand turbulence. So wind turbines need smooth laminar flow to work efficiently, and that means they need to be above obstructions. And obstructions, even some distance away, can cause turbulence. Typically about 10 times the height of that obstruction. So if you've got a forest 50 metres from your home and the trees are 20 metres high, they'll cast a 200-metre turbulence zone beyond if the prevailing wind is from the direction of where the trees are. That turbulent wind will cause wind turbines to hunt in terms of their orientation for finding the wind direction. It also causes stress on the blades, particularly horizontal axis turbines suffer from turbulence and wear and tear. And then you've got to consider how regular the wind is too. It might be a weekly event, no wind for a week and then some wind. So wind actually turns out to be A, quite complex, and B, quite expensive. But it's still a viable option in certain locations. Hydro. Now, I've got a bit of a love affair with micro hydro because I've done a few projects, very small ones. Got one here at the co-op where I live. It is by far the cheapest form of renewable energy, but there's a huge but. You need a water source that ideally is continuous, and you need a lot of water, okay? I hear a lot of people say, oh, you could pump the water up to a storage tank and then flow it back down and generate electricity. That's absolutely true. But if I do the numbers for you, our turbine we have at our co-op is a small 2 kilowatt turbine, but it's only running at a modest rate. It's actually running at about 300 watts because of friction losses in the pipe, etc. There's like 700 metres of pipe running to it, and it's got a 70-metre head. Now, 70 metres of head is pretty reasonable amount. You should be able to get a fair bit of pressure and drive a fair bit of turbine activity, but it will consume around 110,000 litres a day, generating 6 kilowatt hours of electricity. 110,000 litres is a lot of water to lose in one day for 6 kilowatt hours of electricity. So unless you've actually got natural flow of water in a stream that you can harvest. In fact, what you're doing is temporarily borrowing its kinetic energy and ideally just returning it back to the same river system, so there's no net loss of water. It's a very cheap form of renewable energy. I know there's quite a lot of micro-hydros in New Zealand, particularly in the South Island. I've visited quite a few of them. And the complaint that I've heard quite often from the owners of those systems is we have too much power. We just don't know what to do with it because it runs 24 hours a day. And it means things like your battery sizing can be really minimal. The battery is only required to store the amount of intermittency in energy demand. So if you've got a turbine putting out 2 kilowatts, only when you're drawing more than 2 kilowatts of power does the battery start to discharge. So yeah, it's a fabulous resource, but rather site specific. It does also mean you've got some maintenance issues associated with it, and particularly if there's a risk of flood, etc., being able to pull the turbine out of flood zones. But New Zealand has a world famous company called Eco Innovation. So in Palmerston North. No, near Mount Taranaki, but anyway, and so they sort of do an amazing job in terms of taking what's basically a waste product, things like a Fisher & Paykel smart drive washing machine, and turning it into a modern, very efficient micro hydro system. So yeah, Michael Lawley from Eco Innovation, he's been doing them for decades. So hats off to innovation in New Zealand. Okay, so that's resource assessment. Let's move on a little bit to accessing electrical demand. Now, I say that this is probably the hardest part of designing for a standalone power system, because unless it's an existing installation that's got some evidence of power usage, like let's say they're being running on a generator. I've had a few of those customers who've had generators for, literally one old guy had generators for 30 years, been running something like about a 10, 12 kVA generator for 30 years. In fact, he had 3 of them. And I said, why are there 3 generators here? And he said, well, the first one died after 10 years, so I bought another one. The second one died after 10 years, so I bought another one. And he just kept on buying them and putting them in the shed side by side. Yeah. Oh, yeah. New Plymouth. Thank you, Charles. That's where Eco Innovation is. You can check them out on the web, by the way, ecoinnovation.co.nz. So, yeah, someone who's been running off a diesel generator has a very unusual energy use pattern. Often they'll only run it when they need to, and so they might run it for just a few hours every day for, appliances, or maybe something like a fridge. They'll turn it off overnight, and the fridge will sustain a reasonable temperature over a 10-hour period or so, and then they'll turn it on again in the morning. But you've got some evidence of power consumption to base your electrical demand on. But the normal approach is, particularly if it's a greenfield site, so they're going to be building, is you need to get the customer to specify what is it that they want this solar, hopefully, or to wind or micro hydro based system to provide power for. So yeah, it's a bit of a tough call. And maybe I'll just talk a bit more of that. So, whoa, where do we go? It's the wrong picture. Too many buttons. So, yeah, where do you start getting that sort of data from the customer? I usually give them what's called a load sheet. So something that they can use to list all the appliances that they plan to install in that building. and try and get as much data about those appliances as you can. Things like what their maximum demand is. So something like a pump, for instance, will have a high surge rating when it starts up and have a lower run power. Those two factors are important. The run power determines the energy use, and the surge rating determines somewhat the size of your inverter system to be able to cope with that surge. So you need both those things. If you can measure stuff, that's a bonus too. I've had a few customers who are currently living on grid, planning on to moving off grid, and I've given them a power meter, little power mate, plug-in sort of 3-pin job, and they plug it in and measure stuff around their home and write it down for me. So that's really useful, particularly things like a fridge. A fridge is, I often say it's the one appliance you buy that you never turn off for its whole life. And it's using power 24/7, and it's got a cycle, so it's a bit hard to tell just instantaneous reading. And it'll typically go through a compression cycle, then rest, and compression, then rest. So you need to have something that will measure over time, and that's what power meters are great for. Even relatively cheap ones, like $50 plug-in ones, will give you a certain amount of energy over time calculation. Now, speaking of fridges, and maybe I'll talk a bit about some tips and tricks on costing, because actually it often just comes down to cost. Can the customer even afford what they imagine they need? I like to have a few tire kicker numbers handy for me when I want to answer a customer's queries about how much this system's going to cost. So let me just bring my little drawing pad up again. Now I have this, and of course this number is my number for the sort of systems I would build. I like to say to the customer that the system build price, that means all of the components, including the labour component, is going to be related to the energy demand. And so the system build price will be approximately $2,000 to $4,000. You're going, gee, that's cheap, Glenn. Wait for it. Per kilowatt hour per day of energy demand, right? So it's all about energy demand. So what does that mean? Why is it by the first start? The first question I get is, what do you mean 2,000 to 4,000? Is that your profit margin? I go, no, that's the days of autonomy. Basically a small battery system, a larger battery system. How many days can you go without having to fall back on something like a backup generator? So that's kind of a flexible range in terms of the customer's budget. So let's say they've got a fridge. And, I like to explain this to them because I'm usually trying to encourage customers to think about energy efficiency before they think about how big a system they need. It's all about getting the energy demand down as low as you can, because that's where all the cost savings are. Solar might be free, but nothing else about it. It's free. The panels, the batteries, the conversion equipment, etc. So let's take a fridge. They've got a 500 litre fridge, and it's a goodie. They've had it for like 12 years. They love it. It does all the things they want, and they want to take it with them off grid. Now, fridges when they're new, perfect seals, the compressor is fully gassed and it runs really quite well. It might be consuming, say, depending on the age of the fridge, I don't know, 1 to 1.5 kilowatt hours a day, but after 12 years, things start to deteriorate. So it's lost a bit of its refrigerant. It's started a bit of wear and tear on the compressor. The fridge seals, particularly around the lower side, have started to leak a little bit, so they're draining a little bit of cold air. And if you want to show someone how to test if their fridge seals are good, just get a stick of incense and hold it at the bottom of the door. And if you see the fridge cold air blowing that incense away, you know it's leaking. So let's say that fridge currently uses about 3 kilowatt hours per day, right? Now to build a system to run just that fridge is going to be 3 times these numbers. So the build price just to run the fridge is going to be somewhere in the realms of $6,000, oh my gosh, to $12,000 just to run the fridge. Right? Isn't that insane? All right. So what about thinking of getting a new fridge, right? A modern 500 litre fridge. So this is the old fridge here. Okay, old. and we're going to look at the price of a new fridge. Now, I often say it's worth going for the highest star rated fridges you can afford because it will save you money very quickly, maybe even from day one. And how can that be? Well, you'll see. So let's say they buy a 7-star 500 litre fridge and it uses 0.8 kilowatt hours per day. And that's a realistic figure, some of those really efficient fridges. That means the build price to run this fridge is now only $1,600 to a maximum of $3,200. What a price difference. Look at that. Even at the lowest end, that's saving nearly $4,400 just by buying a new fridge, which I'm sure won't cost them $4,400. So from day one, they're ahead buying a new efficient fridge. So appliance selection is often where some of the biggest savings come around. And the ones to look at, of course, are the regularly used items like dishwashers, clothes washers, fridges, freezers, and if you've got active heating or cooling, air conditioning units as well, looking at those star ratings, because that's where there'll be some huge cost savings. Okay, hi Dyer, it says prepaid power. Yep, that's what buying an off-grid system is, prepaid power, you're right. And Ray says, hi. Ray, are you on a boat in the middle of the ocean somewhere? You did say you were going on a cruise. I wonder if you got reception. So, yeah, this is my tyre kicker number. So if we come back with, after doing an assessment from the load sheet for the customer and discover that they use 20 kilowatt hours a day, we can then give them a ballpark figure on the phone straight away. Look, it's going to be somewhere between, if you're using 20 kilowatt hours a day, somewhere between $40,000 and $80,000 to build a system for you. Now, like I say, these are my pricings. They used to be higher, so because the system build price has gone down with the cost of solar and batteries. Oh, g'day, Mark. Mark from Brisbane. I hope all's well with you. You've survived nasty Alfred storm up there. I think we've got a bit of your rain, but last time I looked it was like 10 mils. So add a few zeros for what you had. Yeah. Okay, so that's why it's all about energy efficiency. I know energy efficiency doesn't get much glamour. Like trying to sell doing less is not really very easy, because customers often have this attitude that solar panels are cheap and you just sprinkle fairy dust on your roof. That's what I call solar panels, and all your problems go away. To some extent, that's even true, because solar panels have got very cheap, but still energy efficiency should be considered the first form of energy, and that's what I'm trying to push. You should always go for energy efficiency if possible, and that actually rolls through to things like building design. Now, you know, it's unlikely that as someone who sells renewable energy systems, that it's unlikely that you're also designing the home. But if you have an opportunity to encourage good passive solar design at any time during a customer's inquiry into living off-grid, it will pay for itself many times over. So things like insulation, eaves, ventilation, all those passive solar elements are non-electrical, and they can be a very big cost reduction. So yeah, energy efficiency and active and passive solar. So where are we? Okay, going back to my slides. So now we're stepping into the design process. Now, apologies for those who are very familiar with electrical design, but I'm trying to keep this kind of a bit more consumer orientated, just to help people who are not necessarily directly involved in the solar or renewable energy industry understand some of the terminologies. And so we'll see there's a bunch of ways that you can configure systems. You'll hear terms like AC coupled, DC coupled, a switched system, switching from one source to another, a combination of AC and DC coupling, all renewable, so 100% renewable system, or maybe a system with a generator backup. And then for more complex projects or multi-dwelling projects off-grid, microgrids. In fact, I've talked a bit about microgrids on Toolbox Tech Talk before, and I live on one right here at Murumura Co-op. In fact, I'm involved in designing one for a small town in Western Victoria at the moment for something like 150 homes and businesses. So, yeah, that's pretty exciting. So microgrids are probably a bit beyond the reach of what we're talking about today. But let's backtrack a bit. AC coupled used to be very rare because the equipment available was quite limited. But what it means is that you have a solar inverter and you have a battery inverter, and the two exchange energy. Well, the solar inverter exchanges energy through to the battery inverter through the AC network. The advantages of AC coupling: it scales easily, it doesn't require co-location. That means you don't need to have your solar close to your battery system. It can be on another building even. And there's plenty of products that can be AC coupled these days. DC coupled was the only way of building standalone power systems back in the day, because you would have DC coming off your solar panels through a charge controller directly to your batteries. The advantage of DC coupling is it's simple, reliable, and direct. It doesn't require two inverters to work. In fact, it doesn't even require an inverter. Though these days you can get what they call hybrid inverter systems, so they actually have a inbuilt DC coupling inside the unit. And so DC coupling gives you some advantages. It's a little bit more efficient than AC coupling, but I wouldn't get hung up on that. It's a very, very small amount. It is simpler and to some extent more reliable because of the simplicity of the electronics involved. But it used to suffer from scalability. It was hard to build big DC coupled systems and hard to expand them. But those numbers have changed as well. So we're finding now that DC coupled can be similar sized arrays, running at say 600 volts or so, DC coupled to a 48 volt battery system with the appropriate equipment. I'll skip over switch because that's kind of a bit of old school. That's where you might have had a backup generator that you switched the whole home over to when your renewable energy system ran out of juice. That's pretty clunky, and just about all quality inverters these days can parallel with a generator, so they don't have to be switched. They'll just bring the generator online and run their own inverter in parallel with the generating set. Now, AC and DC coupling, what's that about? So AC and DC coupling, it sounds like dirty deeds done dirt cheap. There's a bit of an Aussie joke for you. It's where you have both systems. Now, why would you want an AC coupled system and then as well a DC coupled system? I call it energy resilience or system resilience. One of the challenges for an AC coupled system is that the battery inverter is a grid forming inverter, and the solar inverter parallels with it when it's available. So it needs the battery inverter to be on and generating for the solar inverter to send power to the battery inverter and recharge. So as you can see from this picture here, the battery inverter is basically the man in the middle. Now, imagine that it's winter time in chilly southern New Zealand or Victoria, where I live, and we've just used too much power for the last 3 days because it's been raining like cats and dogs, like it is right now, as you can probably hear, and the battery inverter shuts down at night time. Then this morning is a beautiful sunny day, but the battery inverter can't turn on because the batteries have got down below their minimum voltage, and the solar inverters can't generate because they've got no voltage source to parallel with, and therefore nothing happens. It's a sunny day and nothing happens unless you start that generator and get the battery inverter back online. So that's one of the shortcomings of AC coupled, but adding a very small DC coupled system to that battery, it could even be 2 panels and a charge control. It means that it will start to charge that battery first thing in the morning, and once the battery's raised just half a volt, usually the battery inverter will turn back on and you're back in life. So let's think of that DC coupling as a add-on to a primarily AC coupled system. Running back down through that list there, so renewable only. Now, if you want a 100% renewable energy system, you're going to have to really oversize things, or you have to live by the sun. And I think I said in my little email blast that was kind of one of my tips is live by the sun, because if the sun hasn't shined and you've got a solar system, you're not getting any input, so you need to ramp back your demand. So use less energy, become efficient, and seasonally as well. So particularly in wintertime, you just try to use less energy, or even have appliances that are summer only or winter only. So let's say you've got a range of ways of cooking. You've got maybe gas cooking or wood-fired cooking and electric cooking. You might use electricity as much as you like during summer because you generally have quite an abundance, but come wintertime, or if you live in the tropics, the wet season, you move on to those other reliable sources such as gas or wood. So appliance change can be part of that coping with a 100% renewable system. But generally, and I kind of push this, a backup generator, as much as I don't like them, because yet another thing that can break down, do mean you have a level of reliability, and that's pretty important. So if you choose to go 100% renewable, you have to accept that sometimes you will possibly run out of power. So yeah, black is the new black. Blackout is the new black when you've overused the system. And you really would want one that has a DC coupled component that can turn that back on when the sun comes back. So if you're happy to live with occasional loss of power and be very mindful of your energy use, 100% renewable can be done. And I have seen a bit of a shift towards this actually, because generators cost quite a lot, and they require fuel, and they can be reliability issues and maintenance issues. And so some people go, well, why don't I spend all that extra money on more solar? So rather than spending $10,000 on a generator, I'm going to spend another $10,000 on more solar. Now, that does definitely help with recovery rates of a renewable-only system when there's not much sun around, or when the sun comes back, I should say. But basically, if there is very little sun, like today, it's the middle of the day here and it's dark outside. And I'd say I'd be getting maybe 2% of what my panels can put out right now. So, nothing in really, even if I had a massive system. So, we've got like 80 kilowatts of solar out there, and it's probably generating, geez, I should look it up for you right now, see if I can bring it up on screen. It's probably generating bugger all. 1.2 kilowatts is coming in at the moment off a 80 kilowatt array. So oversizing helps, but it doesn't completely save you from extended periods of poor weather. So there you go. Let's have a look where we're up to. And it's coming back to my slide. Okay, major components, component selection. Now, this is definitely a philosophical thing, but do you want to go cheap or do you want to go expensive? Those are kind of one of the basic choices when you're choosing components for your renewable energy system. Going cheap means probably low reliability and more pain. So if you remember we talked about Maslow's hierarchy of needs, and if you put everything into an electrical budget, or at least a large proportion of your needs into an electrical budget, you're expecting that your system is very reliable. So choosing cheap and questionable equipment can mean a lot of power outages or even complete failures. So quality off-grid equipment really is where you want to head to. And I know it costs a lot more, but when you consider the cost of replacement of cheap products that fail or don't achieve the performance you expect, it's not really wasted money. That picture, by the way, shows a very popular inverter brand in Australia, Selectronic. Selectronic is a 60-year-old Australian company. Wow, it's amazing. That's those brown and yellow boxes on the wall. Those are the SP Pros. So Selectronic have been making inverters for, I think, over 30 years now. They started off as a transformer company and then became an inverter company. And they are a bit of a mainstay of off-grid in Australia and to some extent New Zealand as well. And they tend to be paired in AC coupled mode with something like Fronius or ABB solar inverters. They're very common pairing because they have a integration through comms, so they work together really seamlessly. And they even have a sneaky way of overcoming what I call the black start problem. When your batteries run out of puff in the middle of the night, they have a limp along strategy, which means every sort of 30 minutes or so, they try and start up again, see if there's any power coming in from the solar, and if it doesn't, shut down again. So limp along. So that's pretty clever. And beneath that is some BYD batteries. BYD, very popular, both on-grid and off-grid in Australia. So that's a extra low voltage BYD system, nominal 48 volt. So let's go to initial design. Now, 4509 Part 2 has Appendix A and Appendix B. Appendix A shows you the formulas for calculating a standalone power system from renewable sources, and Appendix B is a worked example. Just to give you a sense of how complicated it is, Appendix A is 16 pages of formulas. And personally, I think it's a bit overdone. I often say, look, if you wanted to exactly size everything, maybe that's the way to go. But these days, with the low cost of solar panels, you can have a lot more wiggle room by just increasing the amount of solar you had thought you needed. So I often say just double it. You reckon they need 10 kilowatts, put in 20. That kind of gets you out of a lot of trouble. So how detailed you want to go in your design process is up to you. But there is software available that can do this. There's various products, some of them free, some of them pay for. My company, Solar Plus, make one of those products. So Solar Plus is actually what that particular diagram comes from that you're looking at the screen at the moment. And it can do both on-grid and off-grid designs. It's got a load sheet built in where you can put the customer's loads in and what times of day they're being used and what power levels and duty cycles and power factor, and it does all the calculations for you. So it's pretty useful. There is engineering equivalents, which are quite expensive and probably need to be an electrical engineer to understand them, like PV-Syst. But having some software to help with the design and kind of prove it for you is really a big plus. I do also run short courses, and I've done a few live streams on Dummy's Guide to Sizing, and I call it the 6 Easy Steps. But it does lack a little bit in the detail for a good design, so you can dumb it down a lot. Oh, I see a question, or Mark says, you were close with the 2%. Yeah, right, in terms of solar, I wasn't I? And Ray says, what would a 240 kilowatt system cost with Cellectronics and 80 kilowatts of solar with Fronius and Power Plus 1 megawatt hour battery estimate? Wow, you really put me on the spot there, Ray. I don't know, $2 million? I don't know. I'd have to sit down and scratch a pencil to find that one out. But what's the purpose? I mean, why 240 kilowatt SP Pro and why 80 kilowatts of solar? So all of that needs to be part of a design decision. And why 1 megawatt hour batteries? So yeah, it's going to be an expensive system, Ray. Is that the next one for your home? I joke not, though. Some people use a lot of power. I had a customer that used 750 kilowatt hours a day for 2 people in a home. That's right. 3/4 of a megawatt hour a day for 2 people in a home. So yeah, some people have big energy needs, and hopefully they've got big budgets to go with it. So there you go. Okay, so needs versus budget. Now that's where as they say, the rubber hits the road. So you've calculated what they need based on their load sheet, and then you do a costing, and then you come up with, oh my gosh, we can't afford that, Glenn. How do you cope with that? So I have a couple of approaches to budgeting, and I'll bring my little overhead in again here. Where are we? So number one would be you budget the system. I call it cost of system. Cost of system is based on energy and power demand. So you actually do all the calculations work how many kilowatt hours per day they need based on seasonal variation to suit their worst resource load mismatch. What that means is, let's take solar for instance. You have plenty of solar energy in summer, but less in winter. What's happening with the loads? Well, it might be that the house uses more energy in wintertime than it does in summer, and it's the worst time to try and provide it with renewables. So the worst load resource match is the design month, coming up with a design month. And so you calculate the energy requirement, the power requirement in terms of instantaneous power to deliver to their appliances, so things like motor startups, and you cost it based on that. This is the gold star approach. This is the one that's most likely to keep you out of court because you've actually done all the calculations based on evidence. Number two is you design the system for a budget. So the customer says, I have X dollars to spend, and what can you give me for that? So this approach means it's up to the customer to live within their means based on their budget. And it can be painful because you've already gone through the discussion with them and realised they needed this design, but their budget doesn't meet it, so they're going to get something less. So they're going to have either some hard choices to make. An inferior system, a less reliable system perhaps, or even just a smaller system that's going to conk out regularly, particularly in wintertime when there's not much renewables. And the third approach is a pre-built system. Now, this is your online sales approach where you might see this is our 10 kilowatt hour day system and it costs $25,000. And this is our 25 kilowatt hour day system and it costs $45,000, etc. And so the customer just chooses one. They go, oh, that one sounds like it'll do. That's pretty good. I'll take that one, mate. Once again, they've basically, without any assessment of their energy needs, chosen something based on price. Now, there's nothing wrong with any of those three approaches, but there are consequences. And I try to veer people away from these last two options because if you're involved in this professionally, you can get yourself into a lot of trouble. You better be sure that all of your contract is very clear about what you're providing them, and you're not promising any performance because if you don't know what their energy demand is going to be, having a budget that's too small will not help. Okay, so what have we got here? Ray says that system was for an off-grid remote EV charger. Okay, right. And 30 persons town that's on diesel. Thanks for that, Ray. Okay, so coming back to my overhead. Switching myself over there. Here we go. All right, so we've got about 10 minutes to go. This slide presentation I'm giving you, I think there's like about 33 slides in it because it was a long course. I ran it over 2 days online. But this is just a bit of a sneak peek at some of the key aspects of going off grid. So some of this is kind of boring, but really important. So for instance, having good documentation, or having documentation full stop, has been mandatory requirement ever since the earliest versions of our standards. So both the PV array 5033 for standalone power system design 4509 part 1 installation, and now the battery standard 5139 all require documentation. It's a mandatory requirement, and it lists I think I've just shown a part of the list there on the right hand side. Those things are part of the mandatory requirements. Why is it such a big deal? Because you're actually building an energy system. It's not just you're selling them a fridge and here's your manual for your fridge, don't put hot foods in it, don't hose it down, whatever. You're building an energy system that needs some awareness, because the person owning and operating the system might not be very experienced. They might just basically expect that it's going to work. So you need to explain things like how to shut the system down, what maintenance requirements there are. And some of these things actually, even though they're mandatory and you might go, geez, it's a pain to do this, it can get you out of trouble. For instance, providing a maintenance schedule protects you against customers saying, oh, it broke down, and it's your fault. Well, we told you that you needed to check your batteries every 12 months, at least get someone to come and check the integrity of the system, or every 2 years or so, to ensure reliability. And if they don't do that and it fails, well, it's not your fault. You've actually put that in your maintenance schedule. So things like connection diagrams and commissioning reports are really useful for when there is a breakdown and an electrical worker has to come to site who may not be the person who built it. They need to know how it's configured. And if they have to spend a day just looking at wires in conduits and under walls to try and work out what's going on, you're just wasting money. So an electrical connection diagram is really important. So there's a whole lot more. And of course, safety information, things like warning signs, where there's a hazard, whether it's toxic fume hazard, a chemical hazard, electrical hazard, all those things need to be identified and signed appropriately. So energy demand, I think we've kind of talked about this already, which is why you need to customer complete a load sheet. And you know, if you get them past the tyre kicking phase, which is you've given them a rough estimate based on energy demand. So let's say they thought they used around 20 kilowatt hours a day, because that's what it says on their power bill, and you told them it's going to cost you somewhere between $40,000 and $80,000, and they're still interested. Now send them a load sheet to complete. If they can't even tell you what appliances they've got, they're not worth having as a customer. They're just going to be trouble. You're designing blindly for them. So getting that information is really important. Understanding what the maximum AC and DC demands are. Now, mostly these days it's all about AC power, but sometimes there are some DC appliances. Lighting was one that was quite common to have a DC appliance, but these days not very common. I actually dual wired my house when I built it 12 years ago, so it's both got AC and DC wiring in the ceilings for the lighting, and I only recently switched over to AC lighting because there's so much more choice now with very efficient LED lighting. Surge demand is understanding the problem appliances, and particularly what we call simultaneous surge demand, or coincidental surge demand. For instance, you might think, oh, well, the pump surges, up to like 3,000 watts when it starts, so that's the only one we need to consider. But actually, the pump surges because you've got the washing machine on, and the washing machine's got a heating element in it, and so the two will be coincidental demand. So looking at what those might be will affect your inverter size selection. And you can burrow down into things, understanding the difference between real and apparent power. So the difference between kilowatts and kVA, those become important because inverters actually have to deliver both of those things. And understanding when an appliance is being used. So that all factors into your load sheet. So there you go. There's a sample load sheet. Homework, complete this load sheet for your proposed system design. Well, that's because it's for a course I ran, but you can choose it as homework. But really, I just suggest you get a Word document up or even a spreadsheet document up and make some columns. Columns for the appliances, the quantity of them, the power rating of those appliances, hours per day, and then you can calculate the watt hours. A more detailed one would include power factor, if you understand what that is, and also surge demand. So there's some sample worksheets in ESNZS 4509 Part 2, which incidentally, for the Kiwis out there, is mandatory under the New Zealand Electricity Regulations 2010. So it's not one of those new standards that just popped up in Australia and you can happily ignore it because it's not referenced to New Zealand Electricity Regs. This one is 4509 Part 1 is referenced, so important. Okay, and I think I've talked about this already, which is energy efficiency, jokingly referred to as negawatts, the watts that you never used. Yeah, so energy efficiency is your friend. It is the first fuel, and it is the one that you want to try and emphasize the customer consider as much as possible, even if it means appliance change. And this is the example I just gave of old versus new. And it's really hard sometimes to convince people that that old curvy fridge that they've had since their grandma gave it to them is really going to cost them a fortune to run. It's probably time to recycle it And if you happen to be near New Plymouth, Michael Lawley converted a whole bunch of fridges into an igloo. I thought that was pretty amazing. I think for us backpackers to stay in a giant igloo, and it even got them responsibly degassed as well. So a giant igloo made out of fridges. There's a good use for recycling. Yeah, he's an amazing guy. Standby loads, you probably know this story, things that are on all the time, trying to educate a customer to be efficient. And one of the things about off-grid, certainly as someone who sells them and designs them, is helping the customer learn about their system over time. I often say that your off-grid customers are for life. They don't go away. They come along and 10 years later want to upgrade and their battery system is starting to fail, etc. Or when they first get their system installed, they have problems. They don't understand why it's using more energy than they thought it would be. And this is where it's helpful to explain to people about inefficiencies, such as standby loads and things like ways to avoid them. Motion sensing, using your finger to turn stuff off, even having a remote switch. I mean, I know that entertainment centres are really problematic because often the power point's at the back, you can't get to it. So having a remote switch on a lead can be a nice thing. So there you go. Well, I think we've kind of run to the end of the session today, and it's just a bit of a touch on a very big topic, designing for off-grid. This is a bit of a plug for myself. I do actually have basically this full course online. If you go to solequip.com, under training, you'll see there's recordings of I think it's 4 hours of training covering a lot more than what we've just talked about today. But anyway, I better check that I've covered everything. And oh yes, so next Toolbox Tech Talk is next Sunday, the 23rd of March, 1 p.m. It's still Australian Eastern Daylight Saving Time for me. I think 6th of April is when it ends, so I've probably got one more toolbox under Daylight Savings, and then we fall in line with Queensland. Yay! That'll be nice. And I think I've had a few suggestions. The earth faults on inverters has been sent to me, a few questions about that one. I think I might cover that in the next Toolbox Tech Talk, but feel free to send some ideas into me, things you'd like me to talk about, because I take all my content really from your suggestions these days, because, you've got to keep the customers happy. That's you guys. Well, not even customers. So I'm just going to type it into the chat here, my email address, so you can email me suggestions. And I'll try and include them in the next Toolbox Tech Talk. So there you go. So I think it's time to say au revoir. Okay. See you guys.
Promise you're the same, running for the meds. Show you like my bad